In this Math 30-3 Limits to Measurement video, we will be reviewing the concepts of uncertainty and tolerance. Focus on how these are used when completing tasks as opposed to measurement instruments. Let's say Ms. Majot prints this piece of paper off so Mr. Kapoor can use his scissors to cut these photos out. Previously, we had used uncertainty to refer to half the precision of a measuring instrument, like a ruler. Uncertainty doesn't just have to apply to measuring instruments. We can also use it to describe how good Mr. Kapoor is at using scissors. Mr. Kapoor is able to cut things out using scissors with an uncertainty of plus or minus 0.2 centimeters. This uncertainty doesn't describe a measuring instrument. It has to do with how well something like scissors can be used. Let's demonstrate the concept of tolerance. When Ms. Majot printed the pictures off, she measured the photo of Mr. Kapoor as 4.3 centimeters wide. So when Mr. Kapoor cuts out the picture of himself, the width will be 4.3 centimeters, give or take 0.2 centimeters. The 0.2 centimeter uncertainty doesn't refer to the ruler we used to measure, rather Mr. Kapoor's scissor ability. Let's work on calculating the tolerance. Because of Mr. Kapoor's scissor abilities, we know when he cuts this picture out, we could end up with a width as small as 4.1 centimeters or a width as big as 4.5 centimeters. Similar to the work we did with uncertainty prior to this, we can figure out the minimum and maximum values possible from an uncertainty statement. Whenever there is a range of acceptable values for a measurement, we use tolerance to describe the difference between the largest and smallest values. The tolerance for Mr. Kapoor's scissor abilities is 0.4 centimeters. Notice that 0.2, the uncertainty, is half the tolerance. Half of 0.4 is 0.2. 4.3 is called nominal value in this statement. Nominal is another way of saying middle. 4.3 is the middle of 4.1 and 4.5, our minimum and maximum values. We write the range of acceptable values as nominal value plus or minus half the tolerance. Now, let's use two photos to demonstrate adding and subtracting measurements with uncertainties. Remember, when Ms. Majot printed the pictures off, she measured the photo of Mr. Kapoor as 4.3 centimeters wide. She measured the photo of herself as 3.6 centimeters wide. Once Mr. Kapoor cuts the pictures out, he assumes that when the pictures are side by side, that together they would measure 7.9 centimeters. Not so fast, Mr. Kapoor. We need to include the uncertainty of your scissor abilities. But it's not 7.9 centimeters plus or minus 0.2 centimeters. It's actually 7.9 plus or minus 0.4 centimeters. Let's figure out why that is. Ideally, Mr. Kapoor cuts the accurate width of his picture at 4.3 centimeters. But because of his scissor skills, he could have been off by as much as 0.2 centimeters. This uncertainty applies to Ms. Majot's photo as well. It could have been cut as small as 3.4 centimeters or as big as 3.8 centimeters. So we hope Mr. Kapoor is a talented scissor artist, but he might end up cutting both pictures too small or too big. That's a range in values from 7.5 centimeters to 8.3 centimeters. A range of widths from 7.5 to 8.3 means we have 7.9 centimeters plus or minus 0.4 centimeters. The math for adding two measurements with uncertainty together is add the nominal values and add the uncertainties. It works almost the same way for subtracting the two measurements with uncertainty. Subtract the nominal values, and notice we still add the uncertainties.